Hello everyone. So connecting to the talk that Mark Oliver just gave, I'm part of SP10 also, Neurorobotics. I come from Karlsruhe. There are some colleagues of us also. We work together with Mark Oliver. So I'm going to talk today about a paper we wrote. It's called Towards Grasping with Spiky Neural Networks for Anthropomorphic Robot Hands. So what it's about is basically the idea is how is the motion represented for grasping. So the main idea that, or the motivations that we have is in biological systems, especially humans, our hands are very flexible system. They interact with different types of objects, known and unknown. They rely on the proprioception, on the touch sense that we have. So it's like kind of a closed loop system all the time. Like we use the feedback from our hands to shape the objects, to know if it's too heavy, if it's slipping away. It's a very efficient system. Like the motoric of the hand is impressive. So for this work, we took inspiration from biology. On the one hand, we implement everything in spiky neural networks. We have a hierarchical motor architecture to describe the hand motions. It's based on motor primitives and muscle synergies that represent coordinations between different muscles. So this is the general architecture of our approach. The main idea is the following. So imagine a finger, you can abstract the motion to be 2D and planar. So you can move your finger independent if you are performing a task-oriented activity or action, right? So you can move your finger independent if you're grasping an object or if you're just doing it for fun. And you can do it for all the fingers. So the abstraction that we did is like, well, this is a known modeling for the hand. Like we will say, okay, we take this spread from the hand that is not part of the finger, so you have your fingers move in 2D, and they have different degrees of freedom. The thumb has 2, and the other fingers have 3. So we model them in the same way, fingers independently. So we have small neural networks that control fingers independently. And then we have a hand network that coordinates them. So this motion that I'm performing right now is kind of the same motion that I will do to grasp an object, or either it's a pinch or a cylinder or different grasp types. So the motions for the independent fingers are very similar. And then we have, in this way, so this hierarchical representation of the motions in the hand. First shaping individual fingers and then going to the hand. So now this is going into more detail on the finger part. Basically, we have 2-layer network. In the input, we have the proprioception, which is here, the joint states. And we have a target direction vector, which is telling the finger in which direction it has to move. It's normalized. And the output is the deltas that control the changes in the joints. This is pretty much everything. And the connections here are all-to-all plastic, and it will do supervised learning. We do motion capture. I'll show in the video later. We do motion capture to get demonstration from humans. So we have the trajectories. We have the trajectories, and we just bias the activation there until they learn. Important there is the method is STDP based. So we just bias the threshold until the activation is there, and then we remove the teaching signal. We have a mechanism for tactile feedback that stops the motion if touch is detected. And then for the hand, we have the same approach. The representation of the hand is more complex because the output is the direction vector for every single finger. We have a grasp type ID that identifies the different types of motions you want to perform in your hand. And then your hand network takes care of activating individual fingers because there's a lot of correlations between the motions that you have in your fingers. As I was saying, your finger motion for this is the same as for grasping a cylinder. We had to add an intermediate hidden layer to perform a sparse representation, which will project the input to a higher dimensional space. And then from that layer, we will learn here all-to-all plastic, the same way we did before. And that will be the network architecture. So for experiment setup, we have a closed-loop system. We have gazebo, and then we have robot hand as the embodiment. Then we encode the feedback and proprioception from the robot, haptic and joint states. We pipe that to the Nest simulator, and we decode the motor commands for the individual fingers. And we have a motion capture system in which we perform like demonstrations with the hand to get like the synergies between the joints. And this is how it looks like. So we tested in the real robot and in simulation. This is the cylinder grasp. It's accelerated and it's not continuous control. What's important there, the detail is the following. We are taking the raw output, spike output from the network and decode it to commands. So we don't have muscles on this approach so far, and which you can see it very clearly here on the simulation. Because in the real hardware, you always have these low-level controllers that smooth it a little bit, and then you have like this post-motion. But in the simulation, you can see it very good. So for later work, we are working right now on putting a muscle model there that will like smooth the control from the neural network. And what you saw at the end there was the motion capture system that we use. We use a leap system, and we created the GUI to know that it was grasping the objects. And yeah, that's it. To finalize, we use a spiking neural network to control robots, both in simulation and the real robot. Biological inspired hierarchical architecture. Motions represent as synergies between different joints and muscles. And that's it. So if you have questions, I'm open for them at the end. Thank you very much.